that change the state of the system, and then sensors measure it again. So this is the classic idea of feedback control. But we're not able to use that classic idea when we're thinking about networks. So a lot of the networks we want to control, like the internet or the power grid, have millions of degrees of freedom. So full control is not feasible because we don't have full knowledge of the system. And we also know that a lot of models in the world around us and systems in the world around us are self-organizing. So that means that they have unanticipated behaviors that we wouldn't have anticipated, and they don't respond to control interventions the way we would think. So a lot of what we want to think about is, what do we want to control? Do we want to control every degree of freedom, as in classic ideas of control theory? Or do we want to think about microscopic versus macroscopic control? So, for instance, macroscopic control would be thinking about how many people are infected during an epidemic event, whereas microscopic control would be trying to understand which particular people are infected during that event. And we might want to just steer the system towards a class of behaviors instead of controlling every single degree of freedom. So for the last few years, I've been working with Mario Di Bernardo and Yang-Yu Liu, and we've organized a series of workshops trying to understand how we're going to control these systems where the nodal dynamics are very complicated and nonlinear, and the networks have non-trivial structures. So we have a review article, a perspective piece that appeared last year where we've been diving into these issues. And I just wanted to touch very quickly upon some high-level approaches for controlling networks. So one of the main paradigms that we've seen for controlling complex networks is the idea of structural control, which was invented in C.T. Lin by C.T. Lin in 1974. And it really allowed a breakthrough in 2011 from Yang-Yu Liu, Laszlo Barabasi, and Jean-Jacques Slotine, where they took this idea of structural controllability, that all you need to understand is the structure of a network. And they were able to marry this to classic notions from statistical physics using spin glasses. So they used the cavity method from spin glasses to try and understand which nodes had to have control signals put into them in order for the entire network to be rendered controllable. So great things happened from that, but it assumes a linear time invariant framework. So it assumes that my nodes have a linear dynamics. And as we've seen, nodes can have very nonlinear dynamics. So real world networks aren't going to be described by these simple linear paradigms. There's also really beautiful ideas dating back to the late 80s on controlling chaos from Ott Gergobi in New York, where we thought about controlling low dimensional systems by taking advantage of the complex structure of chaotic oscillators, chaotic dynamics, chaotic attractors. But they have very low dimensional systems. And Adilson Motter and his colleagues had been extending this idea of low dimensional chaos to think about kicking systems at just the right moment in time for them to move from one basin of attraction to another basin of attraction. But again, it requires low dimensional systems, and we want to control massive, nonlinear, high dimensional systems. There's been a lot of recent advance in thinking about data-driven discovery of control. So part of this is led by Steve Brunton and Nathan Kutz, where they introduced a method called SINDI, which is trying to identify sparse representations of systems from their data. So you start from data and you extract simple equations that capture the characteristic behaviors of these systems. And you can map out basins of attraction and try and think about small interventions that kick you around. And they wrote a very beautiful book that came out in 2019, Data-Driven Science and Engineering, where they talk more about control theory from these data-driven model discovery. And I have personally worked a lot on phase transitions and control interventions, trying to think about the emergence of large-scale connectivity in a network and how we can take a classic idea and delay the emergence of that large-scale connectivity But what we find is that if we delay the onset of connectivity, it happens in a bang very rapidly. And that's something that we've called explosive percolation. So we can take a classic phase transition and delay the onset of the phase transition, but by delaying the onset of the phase transition, we make it happen in a very abrupt manner. And this has sparked a lot of follow-on work, and I'm very proud of recent work with Comroll in the room with you there, where we've been looking at classic notions of percolation on networks and revisiting their universality classes. So work in progress that's very exciting that we're hoping to share with you very soon. And there's also been a lot of work that I've done on control of self-organized criticality. So basically, we find that we can have a control parameter where we try and trigger cascades all the time. So if we trigger cascades all the time, we only get small cascades, but we never have a period of behavior of the system that avoids cascades. And if we avoid cascades at all costs, we can delay cascades, but when they occur, they're very massive. And then we can think about trying to control social networks as well. But and that is certainly a large open question. So there's a lot of opportunities. So there's a lot of opportunities to think about bringing that classic notion of feedback from control theory into physics. And there's a lot of opportunities for taking statistical mechanics, statistical physics, and bringing that in control theory. So these driven far from equilibrium statistical physics models like self-organized criticality, the KPZ equation, the asymmetric exclusion principle, all of these offer a lot of wealth of brand new paradigms for trying to understand control. And of course, a lot of things like machine learning and artificial intelligence and trying to think about hybrid treatments as well. And so I just wanted to point to our article once more if you're interested in diving more into this review about controlling these complex networks. And to conclude, modern systems are made of interconnected complex systems. They're socio-technical, cyber-physical, eco-social, and we see a lot of emergent interactions. So when nodal dynamics and network structure conspire, we can see decoupled states that defy physical coupling. We can look at when we bring oscillatory dynamics and cascading failures together and see the emergence of Dragon King light failures and a lot of opportunities for controlling complex networks. So I wanted to thank you for your time and your attention and allowing me to participate remotely and give you a little flavor and overview of some of the work that is ongoing in the field of statistical physics and complex networks. So thank you so much for your time, and I'll thank my collaborators as well.
Thank you, Riza. Can you hear me all right?
I do hear you, yes.
Okay. Thank you for a wonderful talk. The talk is now open for any questions from the audience. Okay.
Yeah, so you talked about sort of macroscopic control and microscopic control. So is it true that like macroscopic control should in some sense be easier because like at least at the macroscopic level we find that microscopic chaos is sometimes quite irrelevant, right? I mean, because you get predictability once you look at the macro scale. So is it true macro control is kind of easier to do?
I would totally agree with that. That, you know, it's sort of like statistical physics. We think about parameter control. So I change the temperature and I can have things condense to a solid or melt to be a liquid. So we think about a parametric control where we're just concerned about the macro state of the system. So if we just care about the macro state, we're going to have a much easier time controlling systems than if we care about individual microstates. So it's certainly going to be a better place to approach systems from statistical physics, thinking about macroscopic degrees of freedom. But it's certainly a little bit about perspective as well, because you know, we care about minimizing the number of people who get a disease. But then when it becomes personal, we want to minimize the number of acquaintances we have that have a disease. So there's a little bit of a perspective issue there as well. but certainly macroscopic control should be a much easier thing to tackle than microscopic.
Thank you. Are there any other questions? Yes.
Raisa, what I understand, the Dragon King usually appears due to the bubbling, as you see in the share market. Also, the bubbling during the across the synchronization manifold. So, this I understand the mechanism of origin of Dragon King behavior. But how is you look at it from the point of view of the SOC? So, this is my question.
Great. So the bubbling behavior is really part of the self-amplifying mechanism. So that's what we found really distinguishes Dragon King failures from any other kind of failure, that once you reach a critical failure size, the failure has weakened the system so that the whole thing collapses. There's still open questions about what happens in the thermodynamic limit. And maybe we need to have finite size systems for these self-amplifying mechanisms to kick in. But I would argue that any system that we are interacting with in a network in the world around us is finite. So social networks can only be a few billion in size. And then the question was to also contrast it with self-organized criticality. And I think that there are some real subtleties there about looking at the asymptotic limits. So SOC requires infinite system. So we're looking at phase transitions in the classic sense and the balance between dissipation and driving, taking us to the critical point. So I think that it's a very futile, very fertile ground to be looking at the interactions between the two, as the self-organized criticality lets us understand balancing trade-offs, and then bringing in finite size effects can let us see when balancing those trade-offs might lead to Dragon Kings instead of power laws.
Thank you. Raisa, I have to ask you, why is it called a Dragon King?
It was an idea that was originated by Didier Sarnet, and he was thinking about Black Swan. So a Dragon King, why is it different? So he called it a dragon because the dragon has a different underlying mechanism that gives rise to it. And then a king because they're very dominant. And Didier is from Paris, and he was thinking about how Paris is a city that doesn't obey Zipf's law. So dragon because it's distinct from a swan, has a whole different kind of underlying mechanism that gives rise to it, and a king because it's so much more massive.
All right, thank you. I guess that makes sense. Any final?
I have a question.
Oh, yes.
Yeah. So this is a beautiful talk. I'm not an expert on network models or physics, but let me ask something from a kind of like a outsider's point of view. So look, listening through your talks, I was thinking, since you talk about critical phenomena, phase transition, and all of that stuff, so this is kind of in a classical thermodynamic statistical mechanics sense, as I understand the way you put together these models. So I was thinking whether some of these network machineries developed in your field could be modified to apply to explore, say, quantum phase transitions, where the phase transition is not driven by thermal fluctuations, but pure quantum fluctuations at, say, t equals 0. And then, because I see you also talk about analogy with spin glass models and stuff, but also kind of in a classic or quasi or semi-classical sense. But then I was thinking, along that line, I was thinking whether there are analogs of quantum spin liquids, that's not spin glass, where you have many-body entanglement of different patterns. So it's connecting to quantum information, entropy, and all of that stuff. So whether the network science, all these developments that has been going on in the field, whether that can help this other quantum entanglement network field. This is a very broad question from a very
Thank you. Thank you.
outside.
That's a very deep question with a lot of exciting opportunities that lie ahead. So I think that there could be some very fertile areas for investigation. I think one challenge would be to think about how the statistical physics approaches think about asymptotic systems. And when we're wanting to look at quantum systems, we're usually looking at trying to analyze small systems. As you said, though, many body physics as well will be an important role to play there. I'm very interested in how fluctuations amplify across systems. And I think that there's a lot of great room to be moving forward in that
So
area.
I just did. I mean, I understand your point of view. I just did not mean. There's just a quick clarification that not just finite quantum many-body systems. I was thinking also large in quantum many-body systems. In that case, it's quantum field theory, right? So then it's quantum field theory has mapping between statistical mechanics and all of that as you change dimensions and all of that. So I feel a great feature of network science to come in merge with quantum many-body physics, large in limit and approach, the quantum information science, topological quantum field theory, all these things. So this is, I see a very bright, exciting future.
I totally agree with you. And especially with like the Nobel Prize just going to John Hopfield and Gregory Hinton and Jeffrey Hinton. And I see that there's a lot of opportunities for thinking about these spin glasses and encoding memories and thinking about the non-local interactions that can happen. So I agree with you that the future seems like there's a lot of really deep questions that we could start exploring in that space.
Yeah. Thank you.
Yeah, Professor Rice, I have got a very silly questions. Some slide shows the telegraphic lines and all that. What do you want to show by showing I saw some slides showing telegraphic communications and all that. What is the purpose of showing this sort of
telegraphic communications? So here, this slide. Is that what you mean?
No.
The telegraphic communication. So I don't know if I showed anything about like action at a distance, which would be really great. So I'm not fully following your question.
Okay. You showed some pictures showing some pictures showing telegraphic lines or all that there.
Oh, I see. I know this. Yes.
Yeah. So that's it.
Yes. Thank you. So this is looking at an electric power grid, and so electric power grids have cascading failures, and they follow power law degree distributions. And so these models of SOC are often used to describe failures on electric power grids. And they neglect those underlying synchronatory dynamics of the generators. So the generators on power grids need to be oscillating in phase with one another. So it was to motivate our study.
Okay. Thank you.
All right, thank you very much. Let's give a final round of applause for Riza and her talk. Thank you.
Thank you so much. Sorry I was a little over time.
We have the next slide queued up. Okay, we have Ueda.
Yes, I'm here. Online.
Welcome. Okay, so we are now going to shift to our next talk.
Can Can I share the slide?
Let's see, can we get the slides transitioned over?
So do you see the slide?
Yes, we can see your slides now. So I'd like to introduce our next speaker, Masahito Ueda, who will be speaking about symmetry breaking and topological excitations in spinor Bose-Einstein condensates.
Okay, let me begin by congratulating Dhaka University for the centennial anniversary of Bose-Einstein statistics. It's a great honor for me, and I'd like to thank the organizers for giving me the opportunity to give a talk at this prestigious conference. Over the past 100 years, the legacy of Bose has developed into a great source of physical phenomena, and in particular, the very original idea of Bose about quantum statistics motivated Einstein to discover the most fundamental mechanism of superfluidity and superconductivity, namely Bose-Einstein condensation. Here, I'd like to talk in particular about topological quantum phenomena in spinor Bose-Einstein condensates. So this is the outline of my talk. I will begin by reviewing what's topology. I will then discuss the hierarchy of symmetry breaking and the dynamics of symmetry breaking and the nucleation dynamics. I will present three distinct features that enrich topology of spinor Bose-Einstein condensates. I will illustrate examples of topological excitations, such as fractional vortices, non-abelian vortices, and knots before presenting the conclusion. Let's begin by explaining what's topology. So topology concerns universal properties that are invariant under continuous deformation. For example, T-ball is topologically equivalent to a pancake filled with sweet bean paste. On the other hand, a mug is topologically equivalent to a donut because they have one hole. In quantum mechanics, the topology is encoded in the phase of the wave function. The filled pancake is topologically equivalent to a uniform phase. The ground state of a superfluid helium-4 and the conventional superconductors belong to this category. In contrast, a donut is topologically equivalent to a 2-pi phase winding. A vortex state of a superfluid helium-4 and the chiral p-wave superconductors belong to this highly non-trivial topological objects. Atomic gas BEC are ideally suited for such phase engineering. The beauty of topological concepts lies in the fact that they are invariant under stretching, twisting, and compressing without cutting or puncturing. They are applicable to any objects, regardless of the underlying physical processes, and independent of material-specific properties and details of the interaction. They are also robust against local perturbations and caused by impurities and defects. Atomic gas BEC is a cornucopia of symmetry breaking and topological excitations. This is because the system involves energy scales which differ over 5 orders of magnitude in atomic gas BEC. The largest energy scale is actually the Zeeman energy, which causes global spin precession and the quadratic Zeeman shift. Spin independent and mean field interaction together with the trapping potential determine the distribution of particle density distribution. And atoms has spin, and spin exchange interaction determines the magnetism or symmetry of the spinor order parameter. The smallest energy scale is a magnetic dipole-dipole interaction, which creates spin textures, namely spatial variation of spin orientation. So as we lower the temperature or magnetic field, we observe a hierarchy of symmetry breaking, U1, SO3, and combined symmetries. An obvious but very important feature of quantum gas is extreme diluteness, with atomic density 5 orders of magnitude more dilute than that of the air. So this makes the collision time very long, of the order of milliseconds, and the kinetics becomes important. Therefore, dynamics of phase transition and defect nucleation can be investigated in real time. So this panel shows numerical simulation of vortex nucleation. An initially symmetric BC spontaneously breaks its axisymmetry and eventually forms a triangular lattice, like this, where the color shows the phase of the condensate. And this panel shows the dynamics of spinor BC after magnetic field quench from a finite to a zero magnetic field. The right panel shows the phase and the left panel shows transverse magnetization. Here, blue dots here and there shows spontaneously created spin voltages. The system thus offers an ideal playground to test the Kibble-Zurek mechanism. In fact, the Berkeley group observed the dynamics of spontaneous magnetization of a spinor BC after magnetic field quench. As time goes on, transverse magnetization develops in random direction like this. And if we enlarge, for example, this part, then we see a polar vortex, a polar core spin vortex created by the Kibble-Zurek mechanism. The spinor BC, namely Bose-Einstein condensates with spin degrees of freedom, possess three distinct features that enrich topological excitations. First, magnetic moment of an alkali atom originates primarily from electronic rather than nuclear spin. This implies a large susceptibility of the valence electron to an external magnetic field, which allows local control of spin textures. An excellent illustration of this is an experimental creation of Dirac monopole in a rubidium BC. Here we start with a ferromagnetic BC where all spins align in the initially up directions. As we lower the magnetic field, then the zero of a quadrupolar magnetic field, shown black here, goes from above down to the center of the BC. In this process, atomic spins adiabatically follow the local magnetic field and create the spin texture of a Dirac monopole, like this. Here, M equal -1 component has a doubly quantized vortex, which imitates the Dirac string. And M equal 0 component has a unit vortex, and M equal 1 component has no vortex. The right panel shows the experimental results and the corresponding numerical simulations. So this is the numerical simulation, and these are the experiments. So we indeed find that M equal -1 component has doubly quantized vortex, M equal 0 component has a singly quantized vortex, and M equal 0 component has no vortex. Second, there are combined symmetries. For example, a ferromagnetic BC features spin gauge symmetry, which couples the supercurrent with spin textures. The standard order parameter of spin 1 ferromagnetic BC has three components because spin 1 has three magnetic sublevels. A general order parameter can be obtained by rotating this initially ferromagnetic spinner rotated by an Eulerian angle multiplied by the gauge angle. The result is given by this. Okay. And the crucial observation here is gauge angle and rotation angle appears as a linear combination, so they cannot be distinguished. This means that if you rotate spin locally, the system tries to undo it by flowing supercurrent. And this symmetry can be utilized to convert Berry phase to superflow. Third, the order parameter of a spinner BC features discrete symmetries, as illustrated in these phase diagrams for spin 1 and spin 2 BCs. And these discrete symmetries, when combined with spin gauge symmetry, leads to fractional vortices and non-abelian vortices. So let me discuss these topics later. A scalar BC and superfluid helium-4 are characterized by a scalar phase like this. And the single valuedness of the order parameter dictates that fundamental units of vortex phase must be 2 pi. So this is called an integer vortex, so standard vortex. However, the ground state of a sodium BC is called a polar phase, in which all bosons reside in the m equals 0 magnetic sublevel. The order parameter of the polar phase is given by this global phase multiplied by a zeroth component of the spherical harmonic of the first order, which is actually cosine theta, and features like this twofold symmetry with phases 0 and pi. Suppose that we turn the order parameter upside down as we go around a circle. Then the order parameter changes its sign by pi because it goes upside down. And the single valuedness of the order parameter is met by an additional gauge phase change of pi. And since pi is 1/2 of 2 pi, so this system has a 1/2 vortex. So spin 2 BC has a unique feature called cyclic phase. In this phase, 3 bosons form a spin singlet trio, and this spin trio undergoes Bose-Einstein condensation. So this is very unique. Usually in the superconductors, two electrons form a pair. And in spin 1 case, 2 spin can also form a pair. But in spin 2 cases, 3 bosons can form a spin singlet trio. Because if the spin is 2, then 2 plus 2 gives total spin 0, 2, and 4 because of Bose symmetry. And if the combined spin of 2 spin is 2, then a third spin can cancel this 2 to produce a spin singlet. And this shows the order parameter of this spinner BC, where these 3 lobes has phase 0, 2 pi over 3, and 4 pi over 3. Suppose now that we rotate the order parameter by 2 pi over 3 around some symmetry axis, like this. Then the single valuedness of the order parameter is met by an additional phase change of 2 pi over 3. Therefore, the system can accommodate a 1/3 vortex. So next, abelian versus non-abelian vortices. A scalar BC and superfluid helium-4 has integer vortices, and spin 1 polar BC and superfluid helium-3 A phase have half quantum vortices. All of these has only one generator of vortices. For example, in this case, there is only one symmetry axis, and which commutes with itself. Therefore, vortices created in these phases are abelian. In contrast, for the case of spin 2 BC cyclic phase, there are actually 6 spin rotation axes. For example, this axis, and this axis. And we know that rotation around 2 non-parallel axes do not commute with each other in general. Therefore, vortices created by these along those different axes do not commute, meaning that they are non-abelian vortices. Then the next question is, what's new about non-abelian vortices? First, the collision dynamics become highly non-trivial. There are 3 fundamental collision processes for vortices. So when 2 vortices collide, then they usually reconnect with each other like this. Or they form what is called a rung vortex. So when 2 vortex collide, then they stick together by a rung vortex. So this is another possibility. And finally, they simply pass through each other. So passing through. So those 3 are the fundamental possibilities. For abelian distinguishable vortices from the same species, all of 3 processes are topologically allowed, but energetically most favorable one is reconnection. Therefore, in superfluid helium-4, when 2 vortices collide, then usually reconnection is observed. For abelian distinguishable vortices, such as one vortex from one condensate and another vortex from another hyperfine state of the condensate, then again, all 3 processes are topologically allowed, but energetically most favorable one is actually this passing through. However, for non-abelian vortices, the passing through is forbidden because generator creating this vortex A and the generator creating this vortex B do not commute with each other. Therefore, this and this are not equivalent. And actually, reconnection is similarly not allowed, and only allowed configuration is rung formation. So this panel illustrates the collision dynamics of vortices. For abelian vortices, when they collide, then they reconnect. But for non-abelian vortices, when they collide, then they actually form a rung structure. And they will never reconnect, detach. So let me show again. So when they collide, then they form a rung structure, and they connect the 2 vortices together, and they will never detach. So this is a kind of vortex confinement in QCD. And this panel shows the collision dynamics of the same species same species, when they collide, then they fuse via reconnection. Vortex connection, collision of different species, when they collide, then actually pass through each other. But for non-abelian vortices, when they collide, then they form a long vortex, which sticks the two vortices together. So the collision dynamics look very, very different, depending on the type of vortices. So finally, let me discuss knots in a spinor Bose-Einstein condensate. In spinor BC, there are many proposals for topological excitations. So fractional vortices, one-half vortex, one-third vortex have been proposed. And the monopoles have been proposed and which has been created experimentally. The skyrmions has also been proposed. And these topological objects are all characterized by a topological invariant called winding number. In contrast, knots are characterized by a different topological invariant called linking number. What is linking number? Well, linking number is a topological charge belonging to the third homotopy group and describes the number of times two field loop link. Suppose we trace a circle in a BC on which a spinor order parameter points in the same direction. For example, along this link, they point in one direction, and along this ring, they point in a different direction. And if they link once, like this, then the linking number is called 1. And this is a highly non-trivial mathematical structure, but actually we can show that this can be created in a spinor BC experimentally. The basic idea is to apply a quadrupolar magnetic field to rotate the spin locally so that a knot-like spin structure is formed. And then here, hold your polar BC in a magnetic trap under a quadrupolar magnetic field and wait for example, 10 seconds. Then actually you will get knot-like structure. And this panel shows the dynamical creation and the destruction of knots. Under the influence of the quadrupolar magnetic field, one after another knot enters the BC from its periphery. And the solid circle here indicates the periphery of the BC on the XY plane. The time is measured in units of Raman precession frequency at the Thomas Fleming radius. And the parameter B is 0.1 Gauss per centimeter, and Thomas Fleming radius is about Thomas Fleming radius is about 30 micrometer. Therefore, TL is about 5 milliseconds, so which is experimentally realizable. But how to prove these knots? The answer is actually a little bit complicated. So after this manipulation, we slice a BC like this. So we take the take a look at the slice of BC and do the Sterlinger experiment for this part. And if there is a knot, then you will find a double ring structure in each spin component. So this is the telltale sign of the knot. And our prediction was demonstrated experimentally by Hall et al. So remarkably, they use a rubidium-87 condensate, which is actually ferromagnetic rather than polar. But they prepare the BC initially in a polar phase and did the node creation procedure as I discussed earlier before the dynamical instability of BC sets in. So this is the beauty of atomic gas BC. So even though the ground state phase of BC is polar, you can apply the magnetic field and to initially spin polarize all spins up or all spins down or in a polar phase. Then before the dynamical instability sets in, the state stays there. And within such a short time period, you can do experiment. Here, the first column shows the experiment, while the second and third columns show numerical simulation after and before the time of flight measurement. And the fourth column shows the pre-image of the third one. So we clearly see not like, this is the node, the linking number not like structure, and we clearly see this in the experiment. Okay, so I hope I have convinced you of the fact that atomic gas BC offers a wealth of new phenomena in terms of quantum gases, quantum phases, magnetism, and topology. So we do see the Kivers mechanism with vortex creation and fractional vortices associated with spin gauge symmetry, and the non-abelian vortices for spin 2 BC. And finally, we have knot-like structure. All of them have been predicted and realized experimentally. So thank you very much for your kind attention.
Thank you for the wonderful talk. The talk is now open for questions from the audience.
Thank you, Professor Ueda, for a fantastic talk. I actually had two questions. I don't happen to work in this field, but I was rather curious to see because I was completely oblivious of the phenomena that you have discovered. I mean, you and people like you have discovered in the domain of spinor BC. So one of the things that actually crossed my mind, because you mentioned there are some fractional vortices that you have, and I see that there are phenomena that we actually look in, topological phenomena that we see in quantum field theory also popping up over here. So I was wondering whether you might be aware of something called sphalerons. People had actually surmised that configuration like sphalerons, which actually have half topological baryon number, they exist in standard model. Do you have any such thing popping up here as well, or not?
You mean, so half quantum vortex has been created in spinor BC, but your question is in the context of quantum field theory?
Yes, sphalerons. There are like objects which has like half winding number, which appear in this standard SU2 cross U1, but it also has a gauge field interaction. So actually, a supplementary question I was going to ask, whether these vortices or textures in BC actually exert long-range forces on each other or not.
Oh, no. It's a short-range contact interactions.
So given this, sorry, I'm retracting the first question because now since you are not having long-distance forces, that becomes a moot point right now. Thank you.
I have one question. In the spinor BEC, when you describe spin 1 Bose-Einstein condensate, so there are three fields, three functions for three magnetic numbers. Now, when we move on to spin 2 BEC, would there be a different gauge group bigger than the spin 1 gauge group?
It's essentially SO3.
It is not necessary. But we can.
U1 cross SO3.
So when we have 5 different functions and transforming the symmetry transformation, there would be some. Yeah.
Yes, that's for spin-2 case. However, so original group is U1 cross SO3, but there is symmetry breaking, depending on which phase the condensate goes into. So the order parameter manifold is U1 cross SO3 divided by some isotropic group, which is specified by the symmetry broken BC phase.
All right. Okay. Thank you.
Oh, me? Hello. Can you hear? Am I transmitting? I don't know. I don't
Please press the button.
I suppose this. Okay. Thank you very much. It was very interesting talk. I mean, I'm not in the field, but I wonder this type of experiments with these vortices, can they be done in with type 2 superconductors?
Well, it's a little bit difficult because superconductor has a crystal field. So some C-axis is predetermined by the crystal structure. So you cannot arbitrarily tilt the vortices.
Yeah.
Yeah. So in this sense, it's a little bit difficult. Yeah, I think experimental ingenuity is required.
Oh, okay. All right. Thank you very much.
Thank you.
Yeah. So it's a very interesting talk. So I was wondering, for the non-abelian vortices, do you have any topological qubit architecture possible in these models?
I think this is a very interesting question. And we know that it's non-abelian, and so we can devise some non-trivial gradings using those vortices.
Mm-hmm.
But as far as I know, there are no extensive work to use spinor BC for topological information processing.
Mm-hmm.
Right. So I think this is an interesting new problem, yes, which has not yet been fully explored.
I think it has to do with, I mean, I'm not, my question was theoretical, but I think it also has experimental implementation challenge, how to cross lasers to entangle those vortices and make an architecture that's scalable. So that's experimental. But I mean, theoretically, one could, in principle, probe just, I mean, you don't have to be limited by experimental lack of realization, right? So,
yeah, I think you're completely right. And besides, for unlike superconductors and helium systems, atomic gas BC has a finite lifetime.
right.
Yeah, and
Not going to be useful, but I'm saying toy model building for a quantum simulator type of thing. So I'm not saying it's going to be useful for computing over other architectures.
mm-hmm. The proof of principle experiment, I think, is possible.
Yeah.
But actual applications is a bit difficult.
Yeah. Thank you. Yeah.
Thank you.
Okay, I think we have one more question over here, and then we really should move on.
Can you observe anything like BKT transition for spinor boson condensates? And
yes, it's been observed in rubidium BC. So they prepare to the BC, and quench the temperature and observe spontaneous creation of vortex-anti-vortex pairs. Yes. So it's being observed by France group, ENS group, Jean Dalibar.
I had another question. Is there any attempt to confine the spinor Bose-Einstein condensates on curved geometries? And
I think that's a very interesting ideas, and in principle, one can confine, create an arbitrary shape potential into which you can confine a vortex. Yes. So perhaps experimenters need interesting theoretical prediction about this. If you can predict something interesting, then I think experimenters can do this.
Okay, thank you.
Thank you very much. Let's thank Professor Ueda one more time.
Thank you very much.
And now for the final talk of our morning session, our first morning session, I'd like to introduce Parul Chakrabarti, who will be speaking about J.S. Bose and S.N. Bose, kinship, scientific odyssey, legacy, and beyond. I believe you need to unmute.
Good morning, dignitaries on the dais of the dais, distinguished gathering, my dear students. I thank you all for inviting me in this celebration event. My talk will be quite different from the talk you have heard so far. I will talk on J.C. Bose and S.N. Bose, their kinship, synthetic odyssey, legacy, and beyond. J.C. Bose, father of radio science, plant neurobiology, cosmic unity. S.N. Bose, father of God particle boson. Both are polymaths with a wide range of interest in diverse fields, including physics, mathematics, chemistry, biology, mineralogy, philosophy, arts, archaeology, literature, music, and languages. Their genius transcended boundaries. Both made Nobel Prize class scientific contributions, but none received the prize. J.C. Bose, could perceive presence of cosmic unity long before quantum physics and cosmology could discover the presence of a primary source in all natural phenomena, in all natural manifestation. Bose said, I quote, "In the pursuit of my investigation, I was unconsciously led into the border region of physics and physiology and was amazed to find boundary lines vanishing and points of contact emerge between the realms of living and non-living," unquote. This was his inaugural address when Bose Institute was founded and opened on 17 November 1917. Sir Neville Bolt, Nobel laureate in physics in 1977, opined that, I quote, J.C. Bose is a great scientist who is 60 years ahead of his time.
I'm sorry to interrupt. Could you make your presentation full screen? It'll be easier for us to see.
I think it is full screen here. Can you see now?
It's better now.
Okay, I'm so sorry. Jagadish Bose, you know about his contribution. Even then, to summarize, I said a little bit for the students. His research activities you can divide into three periods. First period, 1894 to 1899, is microwave research. Second period, 1899 to 1904, similarity between living and non-living, that is cosmic unity. And third period, 1900 to 1937 till his demise, plant research, monumental research on planting. And his institutions, he worked, the institution he worked, University of Calcutta, University of Cambridge, University of London, Presidency College, now university, it is university now. S.N. Bose, all of you know, theoretical physicist and mathematician, best known for his work on quantum mechanics in the early 1920s. When he was a reader, later professor at the University of Dhaka, Bengal, now in Bangladesh, he and Albert Einstein developed the theory characterizing such particles, now known as Bose-Einstein statistics, Bose-Einstein condensates. Sir Paul Dirac, Nobel laureate, quantum genius, coined the name boson to commemorate the contribution of Satyendranath Bose in the following: Bose-Einstein condensate statistics, Bose-Einstein distribution, Bose-Einstein correlation, etc., etc. In institution, he worked University of Calcutta, University of Dhaka, and Vishwa Bharati. This is the famous letter S.N. Bose, Satyendranath Bose, wrote from the physics department of the Dhaka University on 4th June 1924. It's a famous letter, all of you know about it. So I'll not elaborate on this. I feel proud of that. S.N. Bose's doctoral students, Purnima Sinha, Partha Ghosh, he is here in the audience. He spoke, I believe, yesterday. Shiva Brata Bhattacharya. Other notable students, Monilal Bhumi, Lilavati Bhattacharya, Ashima Chatterjee, Ratanlal Brahmachari. Purnima Sinha made several publications on S.N. Bose. I'll mention a few. Bigyan Sadhanar Darai Satyendranath Bose, a book published by Vishwa Bharati, Vishwavidya Sangraha. Amar Kotha, this is a famous book on Satyendranath Bose in Bengali, published by Bungayos Bigyan Parishad. Satyen Bose's Byaktitva or Mononer Dhara, this is also in Bengali, published in Desh. I am tempted to say a few words about Purnima Sinha, who was the first PhD student of S.N. Bose and the first PhD to receive PhD from the University of Calcutta. Woman, I mean. Well, she was described as the forgotten scientist who broke the glass ceiling for Indian women in physics. Her doctoral work include X-ray crystallography of clay minerals. She constructed the X-ray machine. Rather, S.N. Bose made her to construct the X-ray machine from the surplus army equipment sold as a scrap on the footpaths of Calcutta after the Second World War. After her PhD work, she worked in biophysics at Stanford University, USA, on the origin of life during the year 1962 to 64. This work was at the interface of biology and physics, studying structures involving clay and bases appearing in the DNA double helix. You know that at that time, Fantastic was going on DNA double helix at the other end of the United States, Eastern end. She found amazing similarity. Being a student, disciple of biochemical science, I found this as an astounding work to find similarity between clay structure and DNA base pairing. Amazing. Besides science, she possessed outstanding talents in literature, art, music. I acknowledge with gratitude information regarding Purnima Sinha I received from Supurna, two illustrious scientists, daughters of Purnima. The kinship between S.N. Bose and J.C. Bose. This is like Guru-Shishya relationship. S.N. Bose, one of the most eminent students of J.C. Bose, who inspired them to dream high in life. Satyan was groomed under the loving care of the Bose couple in Acharya Bhavan. Well, here is Satyan. You can see the mark, and J.C. Bose and other notable students are Meghna Shah, J.C. Bose, then Chandra Bose sitting, then standing from left, Snehomay Datta, Satyendranath Bose, D.M. Bose, N.R. Sen, J.N. Mukherjee, and Sinha. Most of them are foreigners, all of them, I think, except D.M. Bose. Besides their epoch-making discoveries in science, both were very strong proponent advocate of spreading science in mother tongue and literary work in Bengali. J.C. Bose was president of Bangladesh Sahitya Parishad. S.N. Bose, president of Bangladesh Vigyan Parishad. He also started the Bengali science magazine Gyan Vigyan. Now I'll talk about some few words about camaraderie of Rabindranath Tagore, J.C. Bose, and S.N. Bose. J.C. Bose's book of Bhakta, The Unexpressed, a compilation of his literary addresses and writings on visits to the historic places of scenic beauty in India, is still highly admired for its literary excellence. Bose published our Bhakta in 1921, and then he gifted Tagore a copy of this book with a note. আজ জোনাকির আলো রবির প্রখর আলো নিকট পাঠাইলাম তোমার জগদীশ. I try to translate it. Today I am sending feeble light of fireflies to the bright sun, Ravi, Prochoral, bright sun of Ravi. So am I correct? I don't know whether you could follow my translation. I send you today feeble lights of fireflies to the bright light of sun. Bose is also regarded as the father of science fiction writer, and in Bengali first science fiction writer, since he wrote in 1896 first Bengali fiction book, Niruddeshar Kahini Palatak Puvan. This is not only science fiction. Yes, science fiction, but there are a lot of science, surface tension, etc., etc. How can you prevent, the storm on the ocean by spreading some oil or some oil kind of thing, surface tension matter. Tagore found Bose to be endowed with the rare faculty of poetic sensibility and imagination, who appeared to him someone more than a scientist. I quote Tagore, "To my mind, he, Bose, appeared to be the poet of the world of facts that waited to be proved by the scientist for his final triumph," unquote. All of you know that J.C. Bose and Rabindranath Tagore were lifelong friends. But it is J.C. Bose who drew Tagore out of his habitual barrier of the Tagore family rules, strict family discipline and rules. The friendship between Tagore and Bose is considered at par with the meeting of the famous scientist Galileo and the great poet Milton. I am talking from Acharya Bhavan today. Here, Acharya Bhavan, Tagore frequently visited Acharya Bhavan. This is historical residence of Bose in Calcutta. Here they used to sit in these two armchairs. I am showing it on the right-hand corner of this slide, in a cozy room, and exchange ideas on arts, literature, science, philosophy, nationalism, etc. This is the cozy room at Javajon, and the two chairs we have restored here. Well, S.N. Bose was introduced to Rabindranath Tagore by Prashant Chandra Mahalavish, father of statistics in India. This relationship lasted till Tagore's demise in 1941. Satyan's proud mother, Amodini Devi, said that, I quote, it was Albert Einstein who told Gurudev about my son. And Gurudev, that means Tagore himself, asked him to meet him. Tagore gifted Vishwaparita, his only scientific publication, to Satyan in appreciation of his contribution in quantum science. Bose served as the Vice Chancellor of Vishwabharati Tagore Oneness University during the period 1956 to 58. Well, I talk about a little bit about the scientific odyssey, legacy, and beyond. J.C. Bose and S.N. Bose, both are scientists par excellence, with shared legacy in the Indian subcontinent. J.C. Bose's investigation point to one truth permeates the diversity that you see around. I unquote. That's unity among diversity. S.N. Bose's investigation led to the discovery of Bose particle. They have striking similarity in personality, passionate human beings with one for all, including the family members of their bandwagons. Besides their epoch-making discoveries in science, both were, as mentioned already, both were a strong proponent or advocate of spreading science in mother tongue and literary work in Bengali. J.C. Bose was born in Rarikal, Dhaka. It is on my right-hand side. The building is still there. We visited a few years ago. Right-hand corner of the slide, Rarikal. Satyan was blossomed in the then East Bengal, now Bangladesh, where in the premises of Karjan Hall and in the physics department, all in the subcontinent proudly shared the scientific odyssey and legacy of J.C. Bose and Satyan Bose. My apologies for my ability to be present physically in the program. I pay my heartfelt homage from Acharya Bhavan in spirit, but in spirit, from the premises. But I am in spirit in the premises of Karjan Hall, which I visited years ago. On the left side is the Acharya Bhavan premises. Acharya Bhavan is being converted into a Science Heritage Museum now. And premises of Karjan Hall, all of you know. Lastly, I pay my homage to all these stalwarts, the son of the soul, one blossomed here. Pay my heartfelt homage to them, and I thank you all for patience hearing. I invite you, if you happen to be here in this part of the country, please visit Acharya Bhavan Science Heritage Museum. It is a treasure trove of the personal belonging and his scientific instrument, his correspondence, his discoveries, and everything is one describes it is a place where art, science, philosophy converge seamlessly. So my open invitation to you all. Thank you again.
Thank you very much for a wonderful talk. Are there any questions for the speaker? Yes.
Why did you call S.N. Bose the father of God particle?
Well, it is. I didn't coin it. This is the quantum genius. He coined it. The Nobel laureate there, he coined it. I didn't coin it.
Thank you. And I have another question. You said Bose was an advocate of teaching and spreading science in mother tongue. Do you think is this approach really practical in this present world of globalization? I mean, is it more convenient to learn science in one language rather than in two languages?
Well, you can grasp better when things are explained in your mother tongue, then there's no harm to opt for the other language. To go for English is better. In Japan, I have been there in Japan a few years ago, or in Korea and other places. There, they teach in their own language also. So you will grasp the importance or beauty of the science better if you are taught in Bengal, in your mother tongue, whatever it is.
Thank you.
I have a comment on the previous. So the neuroscientists apparently find that if you learn multiple languages, at least two, that makes your neural networks more robust and broadly speaking, more intelligent. So it's not about globalization or picking one language. It's you could do that just to improve your smartness. That's one scientific way to look at it. But it's unrelated to whether you should do that in to pursue science or not. Learning multiple languages will just make you smarter.
Thank you.
All right. Well, if there are no more questions, let's thank the speaker. And I believe we now have a tea break.
Participants, we will have a tea break from 10:50 to 11:10. So next session will start at 11:10. That is session 5. And that session is named after Professor A.M. Harun al-Rashid. We called it Professor A.M. Harun al-Rashid Memorial Session. Okay. Thank you.